number of more specific stuff. Starting with not the normal distribution, but something which to some people might be even more simple maybe. And some would argue it's more normal than a normal. But that's a discussion for after 10 o'clock also. We're going to meet 4 distributions. We begin with this one. The uniform distribution. The word uniform in Danish is also lige, the same, equal. That looks complicated. That looks less complicated. That looks pretty complicated. This looks easy, right? This is pretty uniform. This is pretty equal, right? Here I'm visualizing one example of what we call the uniform, the continuous uniform distribution on the interval between 4 and 5, right? We can mathematically talk about a uniform probability distribution between 4 and 5. It has a constant density. That's the definition of the uniform distribution, that everything appears, every value appears with the same probability, right? There is the same probability to be around 4.1 as it is to be around 4.9. There is the same sort of level of probability of occurrence of events, no matter where we are. And I jump back to this one. This is the kind of syntax we will use, something like this. We have seen it last week already. We say that a random variable x follows the uniform distribution between alpha and beta, and we write it with this syntax here. The density function is a constant function. That's the definition. And for it to be a density function, it needs to have a width that matches the interval, because it needs to integrate to 1. So the area of the rectangle needs to be 1. And for that to be the case, it has to be this side. Then the mean, here's something for the extra math videos also. Because now we can take some of these specific distributions and we can plug them into the formal definition of the mean and the variance, these integral expressions. And then we can see whether we can solve those expressions and or derive something simple when we plug in this. And yes, we can for all of these distributions. I'm not going to do it here. I did it in some of the additional math videos. It's not something we will force you to know about, but for those of you who like the math, it might be nice to see that it can be done. If we plug it in, the mean becomes, not surprisingly, right the middle point in the interval. That's the guess most of us would have come up with, I'm sure. I'm not sure I would have ever, by just by pure guess, that I would have been able to state that the variance, look at the uniform, the variance is 1/12 of the squared length of the interval. I can see that. I think I would have to go through the math to realize that that's the right answer. A little silly example. Let's assume, not friendly to you of course, but let's assume still, that you arrive to my lecture completely, uniformly between 8 and 8:30. Thank you for not doing this. Because what would that mean? That would mean that still within the next 5 minutes, I would have just as many entering the room as between 8 and 8:05. And by the way, you wouldn't start entering until 8 o'clock by this model, right? That's a model of a real-life phenomenon. It's one example of, it's not a model that matches your behavior. And again, thank you for that. But just this is one of those examples. We can put up a model that could try to match some real-life random system that we are interested in. Then we could ask, if we have put our real-life stuff into a probability model, we can start extracting information about this system from the model. Since now we have put it into math, and we can start to get different features out of this just by looking at the math and the probabilities. For instance, what is the probability that one of you guys, a randomly chosen one, would appear between 20 and 830. What's the answer? No trick question. It's 1/3. That's the obvious answer, and which is the correct thing. It could be put into integrals and all, but let's not do it. We could maybe just add, I'm talking about that we are, I think, did I bring it? No, I didn't bring the plot, but it's pretty obvious that if you appear between, let's just model it from 0 to 30, what is the probability for you to come between 20 and 30? This constitutes 1/3 of the area, so that's the answer is 1/3. We could also find these probabilities in R. Like we saw last time, there was a P Poiss and a P Binom. Here is a P unif. P for the probability distribution function, funny enough, right? Whereas the D unif would be the density function. So here I take being, this is alpha, this is beta, this is x. What is the probability of being below 20? Sorry, I take the probability of being below 30. What's that, by the way, in this model? I model it as going from 0 to 30. What's the probability of being below 30?
1.
It's 1. And the probability of being below 20, this is this one. This is 2/3, and now I think I've spent seconds enough on this little example. What is the probability that you come after 8:30? Whoa, an intelligent question to pose.
0.
That is a nice 0, and the R would tell us if we were in any doubt about that. Thank you, ladies and gentlemen. That was the uniform distribution.